Okay, guys, then this will be session 20. We're looking at the doctrine of biblical creation, and we're looking at what modern science has come up with, and we're seeing that what we're learning about living systems is really coming into conflict with the popular evolution story. This idea that living systems can just evolve into being completely naturalistically, without intelligent agency, without intentionality. That doesn't seem to make a whole lot of sense. And where we left off, we saw that this idea that the present is the key to the past, or what you see happening today is generally a reliable guide to cases you haven't observed. We're willing to grant that with some reservations, right? We're not going to follow that kind of thinking if it leads us into conflict with the Bible, since the Bible is the one that gives us license to think that way in the first place. It would be ridiculous, right? So generally now we're saying if we watch certain causes produce a singular effect, we're going to have to do some research to determine which cause was responsible for this effect that we're seeing right now, okay? But if there's only one known cause for the effect in question, then chances are when we come across one of these things, it's very strong induction to say that this was the cause. You know, there's only one known cause for such an effect. And in context, we are talking about digitally coded information systems. The genetic code is it's a code. It's like a computer code. And I know the guys at Microsoft are looking very carefully at the computer code, at the genetic code, and trying to incorporate some of those design principles into their own technology. So, and I heard Stephen Meyer talk about this. He's talking with the guys at Microsoft, and they're looking at how the genetic code expressed on the DNA, it seems to be packaged in folders and subfolders and all kinds of interesting phenomenon there that we're not going to get into today. But one of the guys at Microsoft said something like this: I think someone thought of this before us, you know, when he's looking at the code there. Okay, so living things with their information-rich storage and retrieval and translation equipment, all built right in, and the proteins that's being coded for, and all these amazing systems and structures made of proteins. How did all this come into being? Is it simply chance? Let's think about it. Sometimes you'll hear, I love these pictures I put here, but if you are sitting down to a game of poker, any hand that you're dealt is just as unlikely as any other hand that you get dealt, right? So when we talk to people about the vast improbability of a living system just evolving by chance, typically the evolutionist will say something like this: well, it's just like winning a lottery. What are the odds that a person's going to win the lottery? A Lotto 649 or something. What's the odds? And you say, well, it's so many quadrillion to one or whatever. And then they say, well, but someone wins, right? Even against all those odds, someone wins. And I think they're missing what we're talking about when we're talking about probability here, okay? You get dealt a hand. This hand is just as improbable as any other hand you get dealt. It's just as improbable as a straight flush. I mean, this is the best hand you can get in poker. This is worthless in poker. This is the best you can get. Getting dealt this is just as unlikely as getting dealt this, right? What's the difference, though? You know intuitively that there's a difference here. What is the difference? The difference is this hand here corresponds to nothing. This doesn't correspond to anything. This corresponds to the rules of poker. And it also corresponds to somebody getting money, lots of it. If you're sitting down to a poker game and your opponent continually is pulling, four aces, you don't think, well, that's just probability. It could happen, You know that he's up to something. You know there's intelligent design here, right? And this is design detection. When you see an improbable sequence that corresponds to some independently given pattern, when you see that happen, you've detected. Normally you can detect design there. Okay, do you kind of see what I'm saying, you guys? It's not just something that's improbable. It's something it's improbable, and it corresponds to something totally unrelated, a totally independent pattern, and there's a correspondence. Here's a good example here. I've used this one for some years now, but here's a nice red car. Now let's just suppose I bought that for my daughter Alicia. And so she looks in the driveway and she sees her new red car, and there's the license plate on her new red car. And the license plate is AFT 270. That sequence is just as improbable as any other sequence. It's just the luck of the draw, right? I mean, that's just what you get. That sequence is just as improbable as ARF 519, right? What's the difference? The difference is her name is Alicia Rianne Feeks, and she was born on May 19th. So if she saw that license plate on her birthday car, she would know that Dad picked that plate. She would know that there was intelligent design here in the way this thing works, right? She would have to be totally obtuse not to see that. Well, she actually is sometimes, my daughter. But you see the difference here? It's not just that this is improbable. This actually corresponds to her birthday on her birthday car. And that's design detection, when you've got an improbable sequence and it corresponds to an independently given pattern. And that's what you see in the cell. Improbable sequence, improbable DNA sequence, improbable amino acid sequences making these proteins. It's not just that you've got the DNA with its very improbable code for making proteins, but you already have translation equipment to translate that code and start building as the cell obeys the recipe that's in that code. You have to have all this stuff together in one place. Improbable sequences, improbable structures, they all come together and they accomplish the goal of living and reproducing. And I think we can apply the rules of design detection here to the cell. Make sense? You guys with me on that? Any questions about that? It's kind of important. It's kind of like we call this specified complexity. If you want to write that term down, it's not just complexity. It's specified complexity. Specified complexity. A lot of people they draw a caricature of the intelligent design argument, and they say, "Well, the intelligent design advocates, all they argue is that living things are complex. Complex, complex, complex. That's all they say. It's complex." And what a horrible way to misrepresent what we're actually arguing. Yes, it's complex, but it's specified complexity. Highly improbable things, very complex on their own, that just sort of come together and accomplish a task. Design detection. I heard one, I think it was probably William Dembski that used this argument, or analogy. He said, if I whipped out a coin and I started flipping this coin, or I got you to flip the coin, it comes up heads, you write down an H on a piece of paper. You flip it again, it comes up heads again, you write another H. You flip it again, now it's a tails, right? Put a T now. And you just keep that out. Do that 100 times. What do you have on your piece of paper? A seemingly random sequence of T's and H's, right? See any intelligent design there? No. Just seems to be random. T's and H's. And all of a sudden he pulls out of his pocket another piece of paper, he unfolds it. It's the exact same sequence. Now what were you going to think? I think someone's playing a trick here. There's intelligent agency behind this somehow. You're pulling a trick somehow, some way. You don't believe that this is just fluke. You don't believe it's a random thing. It's highly unlikely sequence, independently given pattern. And that's what you see in living systems. Okay? Now, very quickly, remember amino acids. You remember how that worked? That RNA unit comes, brings a amino acid with it. And it parks itself specific location on that other RNA, that RNA photocopy. Remember? And it brought an amino acid with it. And all those amino acids, they link up to form a big long chain. You need the right amino acid in the right place to make this chain so that the whole thing can fold into a three-dimensional shape and do what it needs to do as a protein. So think about the odds now. The sequence has to be correct. Each amino acid, there could be, you have 20 to choose from, put it that way. In living systems, you have 20 amino acids to choose from. So let's say you get the first two right. Well, what are the chances you'll get the third one right? With each new amino acid on the chain, the probability drops lower and lower that you'll get the right one in that place. Okay? So just to get the right sequence, probability is not on your side. Number two, not only do the right amino acids have to be in the right sequence, but the right kind of atomic bonds need to be made here. These are peptide bonds, not some other kind of bond. That has to be in place as well. Thirdly, they have to be the right shape. Each of the 20 amino acids that you can choose from comes in two shapes, what they call right-handed and left-handed. And all of them in this protein need to be of the left-handed variety. So with each step, the probability gets lower and lower and lower that you're going to get the right amino acid in the right place, right shape, right bond. Now, here's a calculation, and we won't go into all the math because we want to get to other things. But if you read Stephen Meyer's book, Signature in the Cell, he goes into all the mathematics for you. But he's talking about combinatorial problems, because this is what you have here. This is a combinatorial problem. You have to get all these guys right sequence, right shape, right bonds. You've got to get the right combination. A combinatorial problem. Okay? Now, we want to know what are the probabilistic resources that you have to deal with here. Let's say you had a combination lock, like this one. See? 4 bands of numbers, and you got to get the right number, right? The right number here, and then the sequence has to be correct. Otherwise, the lock doesn't open, right? Now, how likely is it you're going to get the right combination by chance? How likely is it you can get the right one by chance? The way you calculate this is to figure out how much time you have and how many guesses you can make in that time. And if you can get within that time more than half the total number of combinations, they say, well, you have a chance now. But if you have in the amount of time that's allotted to you and the amount of the number of guesses you get to make in that time, if you can't even get to half the total number of combinations, then the probability is pretty low that you're going to unlock that thing by chance. Okay? You're with me? Okay. So what Stephen Meyer does, he says, okay, let's presuppose that the universe is actually 15 billion years old. Stephen Meyer believes that too. He's a Christian, but he doesn't take Genesis literally. So he says, let's presuppose that the universe is 15 billion years old. And he says, we can calculate based on, we have an estimated size for the universe, and we have an estimation on how much matter's here, and we know what one event is. One event is like physical action over Planck length or something, in the microcosm of the atom. And he calculates all that. And he goes, this is the number of events that have transpired using these numbers in the entire cosmos. It's a huge figure. And he says, okay, what if every event in the universe's history was aimed at creating just one functional protein of 150 amino acids? And he shows you, in 15 billion years, you are nowhere near half the number of total combinations. Orders of magnitude under that. So in other words, if the entire universe was doing nothing but trying to create one enzymatic protein, one useful protein, it couldn't do it. That's one protein. And you've got hundreds and thousands inside one cell that are coded for by the DNA molecule. So he concludes the universe does not have the probabilistic resources to account for not even one protein. And that's a good, That's a cold slap in the face, I think, for the Darwinist. I don't know how he handles this. I really don't. Chance can always serve as an explanation, but it's not necessarily the best explanation. And I agree with that. So in time past, who's ever heard of the alchemists? Anyone hear of alchemy before? What's alchemy? Well, I have it written here for you. Alchemy was the idea that you could take something like lead, which is abundant and not very, well, I guess ballast, maybe. But lead is pretty stable stuff. It's heavy, it's abundant, and it's not that valuable. But it has certain properties that make it comparable to gold, and gold is super valuable. So the alchemists were trying to find a way to turn lead and other metals into gold, right? Spent a long time trying to make it happen and figured out you can't make it happen. And they gave up. Said, we could probably spend our time on something more useful than this, right? What I think scientists need to do today is to give up on this idea that living systems can evolve spontaneously from inanimate matter. I think that it's like alchemy. You're just wasting your time. You're wasting taxpayer dollars. But you know what? There's some guys like Robert Shapiro. He's an evolutionist. And he is studying origin of life. And this is what he said. Listen to what he says here. When all reasonable chemical experiments run to discover a probable origin of life have failed unequivocally, further, a new geological evidence may yet indicate a sudden appearance of life on Earth. Finally, we may have explored the universe and found no trace of life or processes leading to life elsewhere. Some scientists might choose to turn to religion for an answer. Others, however, myself included, would attempt to sort out the surviving less probable scientific explanations in the hope of selecting one that was still more likely than the remainder. That's a lot of words to say, I will never let God explain this. He said, even if we run every experiment and it's getting nowhere, even if the geological evidence shows that life just suddenly came into being, even if we can't point to life evolving anywhere, I will not, he says, I will not turn to religion. Others, like myself, are going to explore other avenues. We will not allow it. So I kind of think about Elijah. I remember Elijah, and there was hundreds of these prophets of Baal in 1 Kings chapter 18. Remember that? They had this big contest. And these prophets of this false god, they were crying out to their God all day long. They were cutting themselves. They're hoping to get sympathy from their reluctant God. They wanted him to answer. And there's no answer from Baal. Remember that? I kind of think that the modern evolutionist is doing this. He is almost praying to evolution. Show us how you did it. Show us. Oh, Baal, hear us, right? Well, Baal didn't answer because he doesn't exist. And as John Whitcomb says, you have to exist in order to get something done, right? And Baal had this huge obstacle in the way called non-existence. And I think the modern evolution has the same problem. It doesn't happen. It never did happen. And yet the modern evolutionist is going to be like these guys, and he's going to keep trying for it, like the alchemist. I'm not giving up. The Bible says, professing to be wise, they became fools. I think it's foolish. Why are you wasting all this time, effort, resource, brain power, when the God of the Bible alone can account for what you're doing when you're doing science in the first place? Why deny him? So that's basically my argument there for intelligent design. Much, much more we could talk about. Any questions, guys, on intelligent design? Any questions or comments on intelligent design theory? Yeah.
The term natural selection.
Yeah.
Was that coined by Darwin?
Oh, yeah. He used natural selection.
Okay.
Yeah.
And that's still used today.
Yes.
And that part he was right on, correct?
Well,
do you not accept that either?
we accept natural selection. So we accept that all things being equal, an animal that's better suited to its environment is going to survive, and it'll pass its genes on to its offspring. So animals that have their genetic systems are coding for a particular trait, and it's useful in that environment, chances are that trait is going to become dominant there. And varieties of that kind that don't have that trait, if they're in competition for resource, they're going to die. So that's natural selection. We got no problem with that, right? But weird things happen too. You think about a school of fish, and some of those fish might be great swimmers and might be stronger, or whatever. But then a whale comes along and goes, and even the better suited ones are dead, right? So, but generally speaking, we got no problem with natural selection. What we have a problem with is the suggestion that natural selection is a creative process. Natural selection, even the very term implies a reduction, right? A reductive process. You go to the store, and there's all kinds of cans of soup. There's Campbell's and Libby's and name them all. There's all these soup, varieties there, and you choose Lipton. I'm going to choose this one here. Well, guess what? You just left all that other stuff behind, right? If nature's leaving stuff behind, where's the creative process in all this, right? And that's why today the neo-Darwinist is saying natural selection and mutation. Mutation introduces the raw genetic material from which natural selection is going to select. But the problem is, and we just talked about it in this class, mutations are not creating new stuff. Mutations aren't really doing what they need to be doing for evolution to happen. Mutations break things. They cause genes to go defunct. Yes, that produces some variety, right, but you don't just keep on breaking things and hope to explain where these things came from, right? It's a different process altogether, isn't it? So natural selection, we agree, but we absolutely deny that natural selection is a creative process. Yeah, does that make sense to you?
Yeah.
Right. I'd like to get on to, now I'd like to share something with you. Yeah, okay. Here, if you take a look at your outline, I just want to quickly go through some of this. Maybe I'll just use a whiteboard until I need some pictures. And this is all stuff you can research on your own as well. And I think I'll just move my recording device over here too so that folks can hear me. So I just want to quickly go through some of this in short order. And even if we finish a little bit early, that's okay with you, right? Or just keep going, right? Just rove right through the whole thing. Okay, so here we are. We're in point C on page 13, point C. And here we're talking about evidence for a youthful creation. And I've got a few points there. We're going to add a few to that. Basically, remember the dictum of Darwin and Lyell. The present is the key to the past. Remember that? The present is the key to the past. If we hold to that, if we hold these guys to this dictum, then the universe and the earth, obviously, cannot possibly be as old as the evolution story requires. And so I'm giving you some evidence of a youthful creation here. Number one, I just kind of randomly went from outer space down to the earth level here, but number one, supernova remnants. That's number one. So basically, when a star explodes, it becomes a nova or a supernova, right? You've heard this before? And so as it happens, here's your star, and this thing explodes, and it leaves kind of a ring here, right? And this ring expands and expands, and they've got that expansion sort of divided up into 3 stages, 3 or more stages. But it's kind of mysterious that scientists have calculated how often this happens, and they've given us an age for the universe, and yet you put all their figures together, we should be seeing a lot more of these supernova remnants around us. We got strong telescopes now. Where are all the supernova remnants? That's one indicator. It could be a good indicator that the cosmos really isn't as old as they're saying. Because we're watching stars blowing up. But where's the ancient supernova remnants? Where are these things? That's not a bad indicator there. Indicator number 2, comets. Does everyone know what a comet is? What's a comet?
Ice ball, ice and dirt ball flying through space.
Right. It's like usually a comet has a nucleus, usually a big rock, maybe 2 kilometers in diameter, something like that, and surrounded by dirt and ice, and this thing goes whipping around. Basically, you've got the sun here, let's call that the sun, and let's say you've got your planets going around the sun, and these comets are whipping in around the sun like that, very elliptical orbits, right? And as the comet approaches the sun, you see that big long tail streaming out behind it. In fact, the comet goes around this way. Even though the comet's going around like this, that tail is still always facing away from the sun, because solar energy is tearing that comet to pieces. That's what's happening. That's why you see that big, beautiful, spectacular tail. It's the comet being torn apart. Now, there are 883 known comets in the solar system. And we want to know how long these things can last with the sun ripping at them. And Jupiter is like a giant magnet pulling comets into itself. Remember in 1994, comet Shoemaker-Levy was sucked into Jupiter's gravitational field, and the comet ended up getting broken apart into 21 pieces and slammed into the surface of Jupiter, pockmarked the surface. So astronomers got to watch it happen. It was neat. So we've got a couple big vacuum cleaners there in the solar system, and over 800 comets. And we've discovered that at the rate these things are falling to pieces, one of these guys, they're not going to last more than maybe 10, 12,000 years. That's a pretty good indicator that the solar system is not older than 10 or 12,000 years, right? So what's the explanation? Well, we're told that, let's do this. Here's our orbits of the furthest planets. We're told that outside the solar system, there's a shell of comets. Anyone know the name of that thing? Anyone remember? There must be a shell of comets. We call it the Oort cloud. 50,000 astronomical units from the Earth. From the Earth to the Sun, 1 astronomical unit. Earth to Sun, 93 million miles. That's 1 astronomical unit. 50,000 astronomical units away, a shell of comets outside the solar system. Every so often, a star comes swooping past, and it knocks one of these comets loose, and it comes into the solar system, and thereby replenishes these dying comets. Now, you know what the problem with that story is? No one's ever seen that cloud. It's a total rescuing device. There's no evidence it exists. No evidence that any star came swooping past to knock them into the solar system. And even if it did, pretty hard to explain why this part of the orbit, that's called the perihelion, that's the closest part in the orbit to the sun. Why comets are randomly oriented like that. The whole thing here, the orbital dynamics of comets make this whole Oort cloud story pretty unlikely, as I understand it. The fact that comets are still with us is a pretty good indicator that the solar system is not more than 10,000 years old, which is what we believe, right? We have Saturn's rings that are falling to pieces. Saturn, beautiful rings. They're falling apart. And yet they're very, very intricate. One of the rings there is braided. There's like a braided structure to it. I think that's called the F ring, if I recall. Yet it's falling apart. It could not have been there for millions of years or billions of years. Jupiter and Saturn are also losing heat twice as fast as they're getting it from the sun. And yet Jupiter and Saturn are very, very warm planets. At the rate that they're losing their heat, they can't possibly be the billions of years called for by the evolution story. Another good evidence for youthful creation is lunar recession. I've got that as point 5. Lunar recession. The Earth is losing its moon. I don't know if I have a... Can you see that? That's the Earth. Okay. And the moon, here's the moon. Guess what the moon does? The moon creates tides. There's the tide. The tidal bulge. That's the ocean being raised because the moon's pulling at it, see? But these guys are a little off here because, the Earth is spinning, hey? And there's another bulge that's created here. It's not quite as big. So you got two bulges, two tidal bulges. And so the Earth is working at pulling the moon close, but the Earth is also working at throwing the moon away from itself. The net result is we're losing the moon. And if you spin the clock backwards, the oldest this system could possibly be is 1.5 billion years. That's it. That is the ceiling. But the modern evolution story, old Earth cosmology evolution, wants to say the Earth is 4.6 billion years. 4.6 versus 1.5, that's a big discrepancy. And I don't think anyone's ever come up with a good explanation for that. Now, we're not saying that system's 1.5 billion years. We don't think that at all. We're just saying if the present is the key to the past, this thing is less than half the age it's supposed to be. See? And that's a problem, right? That becomes a problem. I think I put on here, okay, you can write number 6 down. Number 6 is the Poynting-Robertson effect. No, small comet bombardment. Number 6, small comet bombardment. Since the 1990s, early 90s, we've discovered that comets are striking the Earth's atmosphere and adding to our oceans. Every 3 seconds or so, 20 to 40 tons of water is being added to the system. We didn't know that earlier than the 90s, okay? But you can just start calculating. At this rate, after 4.6 billion years, all the oceans and more would have been filled up with water just from small comet bombardment. So again, it's another indicator of a youthful Earth, a youthful creation. Number 7 you might want to write is the Poynting-Robertson effect. This is just, once again, you've got a sun here, and there's all kinds of radiation streaming out, solar wind. And this strikes dust in the atmosphere, or dust not in the atmosphere, but dust out there in the solar system. This orbiting dust gets hit, and it slows down. And when it slows down, guess what? It's sucked into the sun. The sun is a giant vacuum cleaner. It's sucking out dust, cosmic dust. Now, if this process has been going on for billions of years, don't you think we'd see something of a segregation in particle size? You'd start to see that. And there should be a whole lot less dust out there, you figure, too. That's called the Poynting-Robertson effect. And what we're seeing there in terms of cosmic dust seems to be consistent with a youthful creation, not a solar system that's 4.6 billion years old. The Earth's magnetic field is declining. You knew that we had a magnetic field, right? I've got that Earth Science point 1. The Earth is losing its magnet. I think since 1850s, it's declined 7%. Something like that, something in that neighborhood. So you can just figure it out. Go backward in time, extrapolate, You can make a graph, say, here is time. Here's Earth's magnet decaying. The time will come when there's nothing left, right? Extrapolate backward. If you go back 20,000 years, the Earth's magnet is so strong, nothing could live here. We basically become something like a neutron star. Nothing could live. Only 20,000 years ago. See? The Earth's magnet. We could look at something like Mercury. Mercury has a magnetic field too. Mercury, the planet Mercury. No one expected Mercury to have a magnetic field. It's small, it's rocky. Scientists believe that magnetic fields are generated because there's fluid motion in the outer core of the planet, right? So you've got a planet here. It's got a solid core, and then it has a fluid. This is fluid. This is a fluid liquid core. They're saying that movement here is generating a dynamo, and it creates a magnetic field. Now, I don't buy that story, but that's current popular opinion in cosmology, in astronomy. But they're looking at Mercury, and they said, well, that's just a dead rock. After all, it's been there for 4.6 billion years. It won't have a magnetic field. Sure enough, it does. They discovered it has a magnetic field. And this is a problem because it should be just a dead rock in space. Now, one of their answers, they said, well, maybe there's some kind of a sulfide there. That might keep the like an iron sulfide. It might keep this fluid longer. And the problem is sulfur is pretty volatile stuff. How did this evolve next door to the sun? See, everywhere you turn, we have a problem here. So Mercury looks youthful too, right? With its magnetic field. Pluto. Pluto is losing nitrogen big time. At the rate that Pluto is losing its nitrogen, the process could not have been going on for billions of years. Okay. And then we just take a look at Earth. Earth has continents. You knew that, right? If I could draw a little thing here. Give your eyes a break from the PowerPoint, but oh man, I got to get new markers, I think. Here's our continent. Here's our ocean. Okay. Guess what's happening on the continents? Erosion. Wind, rain, you name it, the elements are causing the oceans to become filled with sediment from the continents. And there's something like, I think this is correct, it's something like 27 billion tons every year going into the oceans. And if I recall, the collective mass of the continents is something like 283 billion tons. Okay, you can check me out on those figures, okay? I'm pretty sure I got that right. But the point is, at that rate, after 14 million years, the continents should be flat, down to sea level. Okay, now you know what that means? That means, according to the evolutionist time scale, that these continents should have been eroded flat to sea level 5 times over since the dinosaurs were here. Now, why do we still find so much fossil-bearing rock? See, now, one lady, she was telling, I gave a seminar years ago, and this one lady said, John, you don't understand tectonic forces. Yes, the continents are being eroded down, but there's tectonic forces, whatever those might be. Tectonic forces are lifting the continents up. So as the continents are going up, yes, there's erosion, but there's a compensation here. I said, sure, but even if that were the case, the fossil-bearing rock would be gone. You know, you got a dinosaur fossil here. There's his head. So yes, let's say you've got forces, whatever they may be, pushing the whole thing up, but this erosive mechanism is still going, this erosion is still happening. How is it that we can say that there are fossils that go back 3 billion years? They want to tell us they found fossils 3 billion years old, when the continents are going to erode flat every 14 million years. By the way, if you swing the moon in much closer, I mean, who's ever heard of the inverse square law? Homeschoolers, you know this, right? Who's ever heard of the inverse square law? You've got Earth here, moon here. there's the gravitational attraction, right? If you half the distance, you don't double the gravitational attraction, you quadruple it. So can you imagine the moon coming, we said 1.5 was the maximum age for the Earth and Moon system, remember? Bring it in that close. Mile-high tides, smashing every fossil to powder twice a day. That's hard to explain, right? So there's that. With the erosion, you have all kinds of metals and materials going into the oceans, and salt going into the ocean, and basically what's in the oceans today is not 4.6 billion years worth of sediment. Nowhere near. It's like 14 million years, or something in that neighborhood. And again, we don't grant that the Earth is that old. We're just saying it can't be older. Even if we're strict uniformitarians, it can't be older than that. Okay. At the time of the flood, don't you think a whole lot of erosion was happening? Just after the flood, when the waters were going back into the ocean basins, things like Grand Canyon getting scoured out. Oh yeah, lots of erosion. Oil pressures, that's another point you might want to make there. You've got the ground here, and then you got an oil rig, and they tap into a reservoir of fossil fuel. Guess what? When they hit that reservoir, what normally happens? Something like that, right? Pressure, high pressure. But the thing is, the rock that holds this oil in its reservoir, the rock is permeable. So the pressures are being diffused. Okay? So how long can an oil reservoir retain that kind of pressure? I talked to an oil geologist from Texas. He said, in his opinion, 12,000 years. Fits pretty good, what we believe, right? If that pressure is on the decline, and it can't last more than 12,000 years, then guess what? If you're tapping it and it's exploding to the surface, I bet you that trap is not more than 12,000 years old. Yet they want to tell us that fossil fuels take millions of years to form. Okay? I think that's pretty good evidence for a youthful creation. Helium in the atmosphere. We know that there's radiogenic helium is being produced in the rocks of the Earth. Helium. Helium is lightweight, very mobile gas, right? That helium is going into the atmosphere. I got to remember the figures now. It's something like, I don't remember now. I don't want to give you wrong figures. But basically, some of this reaches escape velocity and it goes into outer space. Some of it. Most of it is trapped in the atmosphere. So just a little bit is actually getting out. So helium in the atmosphere is increasing. But at the rate that we're watching it happen, the Earth can't be more than something like 2 million years old. At that rate. You could account for everything that's here at the present rate of helium capture in the atmosphere. 2 million years. See, that's a good evidence. These are geochronometers. That's a good evidence there. Okay. Now, in terms of evidence for the flood, I think there's tons. We won't get into all that, but one evidence is the Earth's stratified surface here. The Earth kind of looks like this. Have you ever drive through the States and you go through a roadway, they've cut through a hill or something, or a big cliff or something like that? The Earth looks like this, right? And we are told that these layers were laid down over millions of years. So the lowest layer is the oldest. They call it Precambrian rock down there, right? This is the oldest. This could be like, I don't know, 3 billion years ago, something like that. And then each layer was laid down. They normally admit it's by water. These are sedimentary layers. Each layer laid down over millions of years. So the highest layers, if there's fossils in these high layers, this is the most recent life to have emerged. The lower down you dig, it's like the further back in time you're going. And you see a fossil down here. Wow, man, that thing is one of the earliest life forms because it's way down low in the rocks, right? Now, some of the problems with this story, very little erosion between these layers. They look like normal bedding planes. Flat, no chemical erosion, no physical erosion. It's kind of funny, right? You kind of expect... I mean, where in the world do you see a complete, perfect geosyncline? They're just flat like a pancake, and then this layer comes straight on top of it. Sometimes they want to say that we're missing layers. They say, well, we're missing some time here. Maybe 50 million years in some places. And yet this fits comfortably on top of that with no sign of the missing years. Stuff like that. We know, and also these are remarkably pure sometimes. You got shale, and then you got sandstone, or limestone, or whatever. They're absolutely pure, like they've been sorted. We know that water will do that. They call that liquefaction. Just shake up a jar of dirt with all the kinds of sediment in there, shake it up, and watch it the water will do that. The hydrodynamic forces there at work. Underwater landslides will do that. They call those turbidity currents. Will sort sediments into those layers. Water will do this. And the Christian answer for why the Earth's crust looks the way it does is most of it's because of Noah's flood. Right? No erosion, missing layers, hardly. Surface features. Sometimes when you excavate, you may find fossil footprints in these layers. Footprints don't last very long. It means that something or somebody walked there, and before those footprints could erode away, another layer was deposited quickly. Not millions of years. Sometimes you find footprints. Sometimes you find raindrops fossilized, or ripple marks, soft surface features. Sometimes you'll find fossils that run through multiple layers, like fossil trees, fossil tree trunks. Bazillions of these things have been discovered. Fossil trees running through multiple layers. Obviously, the layers could not have taken millions of years to form. The tree doesn't stand there for millions of years while these sediments slowly accumulate, right? How long will a good-sized fence post, how long will that last? 100 years? 200? 500? 1,000 years? Probably not. But a tree to stand there for 2 million years? Hard to imagine, Sometimes, like in the Rocky Mountains, and even in Israel, in many places, in the Alps, you see this as well. These rock layers, they do this. Okay? And then all of a sudden, they do this. See that? No fractures. I'll show you some pictures of this. We're just tying those layers together. We're showing that those layers were not formed over millions of years. Slow, uniform process. Let's see. Come on. What's going on here? Here, we're talking about mountains here. Okay. This is the hydroplate theory, but here you can see, here's in the Alps. See this? Look at those layers. See that? They're running horizontal and no fracture. This is the Rockies. Look at this. How could those layers have been laid down horizontally, became lithified, hard rock, and then some sort of compressive force is applied, and they all just sort of bend together like they're made of putty? Now, some geologists want to say, well, that's just creep. You apply enough heat and pressure, you can get rock to creep and bend and warp. That might be so, but in places like Grand Canyon, where you see that in spectacular fashion, you do expect the sand grains themselves to be elongated, and that they're not. So this indicates that these layers were laid down wet. And I mean, this fits perfectly with what we want to say happened at Noah's Ark, at Noah's flood, during Noah's flood. Polystrata. I'll also mention We covered some of this already. Turbidity currents. Some of these layers, like the Tepete sandstone, see, this is Grand Canyon here, see? Each layer, remarkably pure, it's been identified. One of them is the Tepete sandstone. They took a look at the minerals and chemistry of that layer. What kind of fossils are in that layer? What are the grain sizes? All this kind of diagnostic features are being considered here, okay, in Grand Canyon. And you know, that layer, and others, I know the Austin Chalk does this too, there are other layers. You can track that layer all the way around the world. That doesn't sound local. I mean, that sounds like a global flood. I think these layers were laid down during the time of the Genesis flood. So there you are in Arizona, same layer in Wisconsin. It appears again in North Africa, in Israel. I mean, there it is. As far as the fossil record goes, fossils do not take millions or billions of years to form. You can tell because look at all these. First of all, these are fish. You probably realize that. These fish are remarkably preserved. Look at all those details. The layers above them are paper thin. And sometimes the layers will actually, you'll actually get several layers that fill the thickness of the fish, if that makes sense to you. It's like the fish laid there on the bottom, and these layers slowly were forming around him and then finally on top of him. But fish get eaten. They don't just fall to the bottom and lay there for 20 years while they become fossils and layers start, form. They're squished to the thickness of a piece of paper themselves, and all the layers above them are very thin. Obviously, those layers were laid down very quickly and squashed the fish before it could decay or get scavenged. This fish here, look what he's doing. He's in the middle of eating another fish, caught and buried. This is a swordfish. He's caught, buried catastrophically, but he's in the middle of spearing another fish. Some of these fossils are very delicate, like a dragonfly wing, fossil sea lilies and crinoids. These things are very delicate. Jellyfish have been discovered, fossilized. There's nothing to them. Obviously, it seems to me the fossil record indicates sudden, recent aquatic catastrophe. Fits very well with the Noah's flood story. In Germany, we have these supposedly 47 million-year-old turtles. They were found copulating. Right in the middle of the act. Boom, there they were, fossilized. It says here, the article here, from Nature magazine, the notion of a stratified lake works as an explanation for the turtle's fate, the scientist says, but not so well for other fossils found at Messel. For example, bats or birds, or even other small mammals. If the upper layers of the lake were inhabitable, then what caused the death of airborne and terrestrial mammals or animals? The turtles were just part of an ongoing fossil mystery. So you can understand, okay, there was some kind of lake here, some kind of catastrophe killed all these turtles right in the middle of mating, but then you've got bats and birds all jumbled into that fossil logjam. And that kind of thing happens all over the world. You've got a fossil ichthyosaur. This is a swimming reptile. This particular specimen is in the process, or was in the process of giving birth when it was caught, killed, and fossilized. So this happens quickly. These guys are buried quickly, see? Fish accidentally snags a pterosaur and both die. Another evidence here of rapid burial, rapid catastrophic burial. Look at all these herring here. One block of rock here, now hardened into rock. Used to be soft sediment, but all these fish buried together. And you find this all over the world, guys. In Alberta, you find evidence of massive dinosaur destruction. They want to say that there was some kind of huge tropical storm and it killed scores of dinosaurs, huge herd dinosaurs like Triceratops. And now their bones are all jumbled together like a log jam. They said that, the scale of the storm must have been, it was incredible. And I want to say, I think all these local catastrophes aren't local. I think it's one big catastrophe called Noah's Ark, the Noah's Ark catastrophe, or Noah's flood catastrophe. And I'll just leave you with one final thing here. It's kind of hard to be selective here, but flood legends. The Bible says all of us can trace our heritage back to those 8 people off Noah's Ark, right? Doesn't the Bible say that? You just expect that people around the world, ancient cultures, separated by oceans and mountains, they would remember it. They would have a memory of the flood. In Dwayne Gish's book, Dinosaurs by Design, he tells us that there are over 270 flood stories all over the world. In Hawaii, long after the death of the first man, the world became a wicked and terrible place. There was one good man left. His name was Nu'u. He built a great canoe with a house on top of it. He filled it with animals. The waters came up all over the earth and killed all the people. Only Nu'u and his family survived. That's Hawaii. The Chinese have a story of a guy named Fuhai. Fuhai, his wife, 3 sons and 3 daughters, just like Noah's Ark. 3 sons, 3 daughters. Or 3 sons and their wives, rather, in Genesis. He and his family were the only people alive on the earth after the great flood, and they repopulated the world. I'll just give you a quote here from this book, and then I'll be done. This is a book called Ancient Mysteries Revealed. These 2 guys are going to explain all the ancient mysteries that have been plaguing anthropologists. You know what mystery they can't explain? The flood. And what of the world's greatest catastrophe legend of all, the worldwide story of a great flood? The flood story still remains one of the most baffling unsolved mysteries of our distant past. The local flood theory doesn't quite reach to the heart of the flood problem, which is why there are so many similarities to the flood legends globally. We no longer have a natural event that could plausibly explain their origin. So that's the point. If you study these flood legends, all over the world, people groups are separated by oceans and mountains. They don't talk to each other. And yet you ask them about Earth history. Tell me, what do you guys believe about creation and early Earth history? And they're going to tell you about a giant flood that happened, covered the world. Only a few people survived. Sometimes it involves a guy building a boat. I know the Peruvians in South America, they have a flood story too. And guess what? After the flood, someone gets drunk. Now, why would that be? Because across the ocean, they have a story about Noah who got drunk after the flood. See? It's little nuances like that makes you want to think, you know what? I think we all have a shadowy memory of this event that really did happen, the flood of Noah's day. So, okay, guys, I'm sorry I went over time. So much more we could talk about, but that's pretty good for today, right? Okay? A word of prayer, and then we're done. Father, in Jesus' precious name, we thank you for today. We thank you, Lord, for confronting us with all kinds of interesting information that, Lord, we pray will put to good use as we walk through this life. Thank you, God. Seal your truth into our hearts. May we represent you well in the world. In Jesus' precious name we pray it. Amen. Amen. All right, guys. God bless you.